Welcome, ladies and gentlemen, to lesson 3.8 from Precalculus, which is all about the tangent function. So let's get started. So the tangent function is an interesting function. So we're going to use the same setup as the definition for the sine and cosine function, where we have an angle in standard position and a unit circle centered at the origin. And we're going to say that there's a point P where the angle's terminal ray intersects the circle. The tangent function would then be described as the slope of this ray. So y2 minus y1 over x2 minus x1, but x1 and y1 are both 0 because we're centered at the origin. So we just get the tangent is equal to b divided by a, with b is the y-coordinate and a is the x-coordinate. So not too bad there. There is another interesting definition that I found out recently, which is given the same exact setup. So we're given the setup that we have a angle in standard position, and we are given a unit circle centered at the origin. But instead of drawing the terminal ray and where it intersects the circle, we're going to draw a line with that angle. And where that intersects a vertical line through the point 1, 0 on the x-axis, that point is going to be defined as 1, tangent. And that y-coordinate of that intersection is defined as the tangent function. And both of those are actually equivalent, and we're going to prove that in class, so I'm really looking forward to that. So that's all fine and dandy. Let's just recall for a second that in right triangles, we said that the tangent could also be found with whatever the sine was divided by whatever the cosine was, and that still holds true now with the function interpretation and not just the right triangle trig interpretation. So we got a couple of questions here, and let's try our best to answer them. So in the xy plane, we have an angle theta, and its measure is pi over 3. What is the, oh, I misspelled slope there. What is the slope of the angle's terminal ray? So that is basically asking for what is the tangent of pi over 3. So how I go about these and how I go about all of these trig things so far is I draw the triangle. So I'm going to draw a triangle in standard position with the angle pi over 3. And I know from my special right triangles that the smallest side gets the smallest angle. So this would be 1 root 3 and then 2, and I know the tangent is the opposite over the adjacent, which would mean that this is root 3 over 1, or just root 3 would be the slope or the tangent at pi over 3. We can use that same idea to evaluate these other tangents. If you want to pause the video and try them out yourself, by all means, but I'm going to get started here. So pi over 4 is pretty simple because we know that that is a 45, 45, 90 triangle. So that's 1, 1, root 2. And that means we have 1 over 1. So this just turns into 1. 5 pi over 6 is a little bit more difficult. I'm in the second quadrant because we're less than a whole pi, but more than a half. And we're 1/6 less than a whole pi. So what I'm going to do is I'm going to draw a triangle. That's going to be a 30, 60, 90 triangle. Pi over 6. Because we're pi over 6 less than a whole. Smallest side gets the smallest angle. So 1 root 3, 2, negative root 3 because we're going to the left. And tangent is opposite over adjacent. So we get 1 over negative root 3. Now we know that that's not good enough because we have a radical in the denominator. So we actually need to rationalize this, which would turn into negative root 3 over 3. So I just took that negative and I pulled it out in front. It's okay to leave it in the numerator or denominator. It doesn't change the value, but I like it because it looks nicer. Last but not least is 3 pi over 2. That's a quadrant angle, and that is specifically going down. So that point is 0, negative 1, and tangent is defined as coordinate points as the y divided by the x, so it's negative 1 divided by 0, which is undefined. So this is undefined, and that'll come up later. So tangent, because it can be defined as a rational function in some, like not an actual rational function, but has properties of rational functions because it's built as rational, we're going to have these undefined points. So in precalculus, we think more about a function's behavior. So if I think of tangent as the slope of these standard position angles, I can get a better idea of what's going on here. I know that this slope is going to start off at 0 when we have an angle of 0. And then it's going to slowly increase. You can see it's getting steeper and steeper and steeper. And in fact, it's going to get steeper without bound. The slope is going to increase towards infinity. But as soon as I get really, really close to the y-axis, I get huge, monumentally huge slopes until I get to vertical. Vertical slopes are undefined. So at pi over 2, it's undefined. Problem. Now, if I continue with this slope idea, if I draw a slope slightly to the left of pi over 2, it is very steep down. It is a very, very large negative number. And it is actually getting less steep. Even though it's getting less steep, it's going from negative to less negative, so it's actually increasing, weirdly enough to think about. But it's getting less and less steep as we go along until we get to 0 again at pi. What happens now? What happens a little bit after pi? Well, if I actually extend these angles that I've previously drawn, these line segments, to intersect the other side of the circle, I can see that I'm getting repeats. I should repeat all of these slopes. So that's a little weird. What that means for us is that every half rotation of the unit circle, instead of every whole rotation, is going to produce unique values, where if we go around the other half, we're going to get the same values as we got in the northern half. So that changes the period of the tangent function. The period of sine and cosine is 2 pi. The period of tangent is going to be a singular pi, which is kind of interesting. More about the behavior. So because we can define tangent as a ratio of sine to cosine, every angle that causes cosine to be 0 is removed from the domain of tangent. And we can actually see that here. Cosine is 0 at pi over 2, and cosine would also be 0 at 3 pi over 2. So we're going to have to remove them. We can't use them because then we divide by 0, and that causes us problems. And when that happens, when the cosine is 0 and the sine isn't 0, we remember back all the way back to Unit 1 that for rationals, if the 0 is unique to the denominator, that means vertical asymptotes. So when this happens, we're going to end up with vertical asymptotes for tangent. In fact, it's going to have an infinite number of repeating ones, which is really awesome. So I gave you a hint towards graphing sine and cosine with 5 key points. It's how I've always taught it. Tangent also has these 5 key points. So the period starts and ends at 0, but our period isn't as long. Remember, the period starts at 0, at a location of 0, and ends at a location of pi. So like we did with sine and cosine, we're going to split these evenly into quarters. So 1 quarter, it's going to be at 1. And then 2 quarters, it's going to be undefined. 3 quarters, -1. And then 4 quarters, or a whole pi, would be 0, which is kind of cool. So we get this lovely looking graph from the tangent function. And we can see that we have 0, we have, this is a little distorted because this is 3, and there's 1, 2, 3. A little bit weird. This is 1, undefined. This would be -1, and this is 0. So again, the scale is a little off because, again, if you look, 1, 2, 3, 4 high is 3, so a little bit weird. We're like each of these is 3/4, so a little bit weird, but I digress. We can also see that the tangent function is always increasing. Well, the tangent function is always increasing. If I follow along the curve is always going up from left to right. We kind of like, I don't know how many people are familiar with a record player, but the needle kind of skips, and then it's increasing again. The needle skips, and we're increasing again. So the tangent function is always increasing, even if there's a value that is really, really small, and then a value really, really big afterwards. The function itself, the curve, is always going up from left to right, which is really cool. We can define its vertical asymptotes with an equation. We can say that the first vertical asymptote is pi over 2, and then every vertical asymptote after that is a whole pi before or after pi over 2. So if I add a whole pi to pi over 2, I get 3 pi over 2. If I add 2 pi to pi over 2, I get 5 pi over 2. If I take away a whole pi, I get negative pi over 2, and so on and so forth. So we can use that equation to define these vertical asymptotes. And this, again, I don't know if I've mentioned this before, just means that we're adding integers of pi. So the z just means it's integer, whole number, positive to negative. Points of inflection. So the concavity changes from being concave up. If we look like here, for example, it's concave up after the 0, and it's concave down before the 0. So all of our zeros end up being points of inflection because the concavity changes. The domain is also everything except for these vertical asymptotes that repeat infinitely. So how do we write that? How do we write, we have everything except for these things, so we don't really have everything. Well, we say we're going to have negative infinity to positive infinity, except for when x is equal to the equation for our asymptotes, which is pi over 2 plus pi times k for all k's that are integers. The range, though, the range is interesting. So sine and cosine oscillate between negative 1 and 1. Tangent goes from negative infinity to positive infinity and does that an infinite number of times, which I think is really, really cool. So transforming this function, a lot of talking from me, I know. Transformations of tangent apply in very similar ways to the transformations of sine and cosine. So the a, the coefficient of tangent itself, dilates the function, and if it's negative, it reflects it vertically across the x-axis. The b, the coefficient of the parentheses for x once it's factored out, remember it has to be factored out, is a horizontal dilation by 1 over b. It reflects it if it's less than 0. The period changes. Remember for sine and cosine, we said that the period was equal to 2 pi, is equal to 2 pi divided by b. For tangent, because the period is pi, it's pi divided by b. So, makes sense. And the vertical asymptotes change by this weird formula, and I'll write it bigger for you. X is equal to pi over 2b plus pi over b times k. And what that is it's taking this equation that we had before, and we're essentially dividing each part by b. So that's where it comes from. C is a horizontally translated part, right by negative c units, or phase shift. We can still use that language here. And D is a translation up or down. It affects the middle, what would be 0, or an output of 0, right? And I did hand signs with sine and cosine. You can also do hand signs for this one, but it's a little bit weird because you have 0, 1, undefined, -1, and 0. So I really don't do a lot of hand signs with tangent. But you could also just like make a cup for u or something like that. So like 0 up, u down, 0. Whatever floats your boat, whatever helps you encode this a little bit better. So doing all of this, now that we know all about these transformations, and we've done most of them before. I know I'm throwing a lot at you, but some of this we've already established, right? Let's write an equation that represents the vertical asymptotes of the following functions. So before we start, what is default? Default is the vertical asymptotes are equal to pi over 2, because that's the first one, plus pi times k. The change is we are modifying the period. So the period modifier here is 2. We're going to divide each part by 2. So x is equal to pi over 2 times 2, which is 4, plus pi over 2 times k for k in the integers. So, honest to goodness, not bad. If you can remember where the first one is, and it's pi over 2, the rest of them really fall into place. So, tangent here, for this tangent, we remember the default is equal to the first asymptote plus the period. Well, we're modifying the period. So this 2 over 3, we're going to be multiplying the denominator by that. So we get pi over 4/3 plus pi over 2/3 times k. Well, we have fractions in our denominators. We need to multiply by the reciprocal or keep change flip. And we get 4 pi over 3 plus 3 pi over 2 times k. And that is it for vertical asymptotes. It's really not that bad. Again, if you have the default one memorized and the period memorized, you just modify it by the period. in the exact same ways that we would modify the period before. So let's put all of this into practice. So let's graph this function with all of these modifiers. So first things first is I'm going to factor the inside of this function. So I have 1/2 tangent of 2 x minus, and I'm dividing this by 2, so it would be pi over 4, close those parentheses, plus 1. So what's happening is the max and min, the ones in my key points, are halving. I'm changing the period with a modifier of 2. I'm shifting the whole function right, and then I'm moving what's considered the middle up. So let's start with the 1. Let's move the middle up. So let's draw the middle here. And now I personally like to think about key points, and that's just where my brain goes. And if your brain doesn't go there and you have a different way of doing it and you get the same answer, by all means, go with your way. But my way of thinking is I have my x and my y, and my 5 key points for tangent are 0 to pi, and then splitting that up into equal pieces. So we have pi over 2, pi over 4, 3 pi over 4. And by default, we would have 0, 1, undefined, -1, 0. We need to change this. So the first thing that I note is our period. I'm going to start with that. Our period is changing. So remember that period is equal to pi divided by b, which in this case is 2. So that means that if we're starting at 0, we're not ending at pi, we're ending at pi over 2. So we need to change all of these up. The good news is that everything is equally distributed, which means directly in the middle, pi over 4. Directly in the middle of this would be 1/2 is pi over 8, and then we'd have 3 pi over 8. There we go. So that is this part checked off. What do we want to mess with now? Let's mess with the other horizontal piece. We're going right to pi over 4. So what I'm going to do is I'm going to add pi over 4 to each of these. So we're going to start at pi over 4. That looks ugly, but you get the idea. Which means that we're ending at 3 pi over 4. In between that would be pi over 2. In between these two, we've already found that was 3 pi over 8, which is going to make this one 5 pi over 8. So, I get it, there's a lot of stuff going on, but taking everything step by step really does help. So, next up, we are shifting everything up by 1. So actually, before we shift everything up by 1, let's dilate first. So my 1 and my -1 are going to become 1/2 and -1/2. Then we're going to translate everything up by 1. So 0 turns into a 1, 1/2 turns into 1.5, -1/2 turns into 0.5, and 0 turns into a 1. And if I plot these points, that is everything taken into account. If I plot these points and repeat it, I'll end up with my tangent function. So at pi over 4, we have 1. At pi over 2, we have an asymptote. At 3 pi over 2, we have 1 again. In between the 1 and the asymptote, we have 1.5. And in between the asymptote and 1, we have 0.5. We're going to repeat that. So it's unfortunately going to repeat a lot, but it follows a pattern, so that is always very nice to see. And I'm going to cheat. I'm only going to graph the right-hand side of it. So we have essentially this graph here. And I'm doing an awful job of actually drawing the curve, but we get the general idea. I say not too bad, it's tedious. Sometimes it is tedious when you have so many transformations. So if you haven't already, I do want you to try this next one out, but I'm going to start it now. So I know that I first have to factor -3 tangent of 1/2 x plus pi minus 2. So I know, first and foremost, that my period is going to be pi divided by 1/2, which is equal to 2 pi. Which is great, and I'm going left pi. So when I'm making my x, y, I'm going to cheat a little bit, and I'm already going to start at negative pi, and I'm going to end at pi because I know my period is 2 pi. So I'm taking all of that into account. 0 would be in the middle. I know that the middle is going to be negative 2, negative 2. This is going to be undefined. And then I know that it's going to go down instead of up because we have this negative here. And I know that my value is going to be 3 below and then 3 above. So 3 below would be negative 5, 3 above would be 1. And then finally in here I have negative pi over 2 and then pi over 2 because everything is evenly distributed on the x's. So first of all, I'm going to draw my asymptotes, which happen at every 2 pi because that's how the period works. Then I know at negative pi, I'm at negative 2. Pi over 2, I'm at negative 5. So 2, 3, 4, 5. Asymptote. Here is 1. Here is negative 2. Here is negative 5. And then just follow that backwards. So I get these long, dramatic tangent curves. And that is it. So if you have any questions, please make sure you ask. Otherwise, I'll see you in the next lesson.